Hello and welcome to today's webinar, 100% bio-based and safe alternative to ethoxylated amine in antistatic polyolefin applications. Thank you very much for taking your time to join us today. I'm Jana Ingram and I will be your moderator today. I work for Emery Oleochemicals since 2015 as a marketing manager for the business unit Green Polymer Additives. Among other things, I'm responsible for all online marketing activities, for creating marketing collateral such as brochures and advertisements, for organizing trade shows, and also for organizing online events such as webinars. In today's webinar, I will collect your questions that may come up during the presentation. I will also make sure that all your questions will be answered. Today's speaker is Dr. Christian Müller. But before I hand over the microphone to him, I will give you some brief information about today's webinar. After an introduction of our company, Christian will provide some general information about antistatic effect in plastics. He will then give you an overview of common antistatic agents and polyolefins, followed by a comparison of different products, including our test results. The presentation is planned for about 45 minutes. During that time, please ask your questions using the chat function to the right-hand side of your screen. I will collect your questions and we will answer them after the presentation. In case we don't get to your questions during this session, I will make sure to contact you after the event. A recorded version of today's webinar will be available, and you will receive a link to the recording within the next few days. So please send me your questions, comments, and feedback per chat during or after the presentation. Today's speaker is Christian Müller, and I would like to hand over the presentation to him now. Christian, may I ask you to introduce yourself?
Yes, will do. First of all, thank you, Jana, for organizing this webinar and for being our moderator today. And welcome to all of you. My name is Christian Müller. I have a chemical background and I have been working in chemical additives for 10, 15 years now. About half of this time for Emery in several functions for green polymer additives. I'm responsible for new business development and technical marketing, which includes webinars, such as the one today. It is very important to me to mention the findings you will learn about within the next 50 minutes are not a result of my personal work. My sincere thanks go to my colleague Annika Heinrich and her team in our Technical Development Center for generating a huge amount of highly interesting data, which we could use to create this comprehensive documentation. So let's get started with our webinar, 100% bio-based and safe alternative to ethoxylated amine in antistatic polyolefin applications. We will start with a very brief introduction of Emery Oleochemicals. Emery Oleochemicals, as a global company, has 6 business units. All these business units have in common to produce several kinds of chemical products, mainly from natural fats and oils. That is why it is Oleochemicals. Our business unit is Green Polymer Additives, with our brands LOXIOL, Adenol, and Amarox. Next to acylic acids as polymeric building blocks, our products are process and performance additives for plastics, such as lubricants, release agents, specialty plasticizers, or anti-fogging and antistatic agents. We started this business in 1957, so actually when industrial production of plastics was born. In addition to our 3 production sites, we also have technical development centers in Germany, Japan, and the US. As natural fats and oils are our main source of raw materials, many of our products are mainly or fully bio-based. Our vision is to be your first choice in sustainable polymer additives, and our mission is to make materials better and processing easier with innovative additive solutions. The agenda for today is as follows. First of all, why do we need to use antistatic agents and which antistatic agents are used in polyolefins? In the test design chapter, I will introduce which additives were tested how and why. We will go through the big results chapter step by step, and after summarizing and concluding the results, my final slide will provide some key takeaways. I look forward to the final part of the webinar, which is the question and answer session. So please enter your questions, comments, and remarks during the webinar. We will discuss and provide answers afterwards. So why antistatic agents? Most plastics are insulating materials, so they tend to build up static charge, mainly caused by friction. In most cases, static charge is something you do not want to have, as plastic films or any other thin, lightweight plastic materials tend to stick to each other or to another material. This might affect the manufacturing and processing, but also the application of such plastic articles. The static charge can also lead to the attraction of dust, what is something you like to avoid. Another issue is that static charge might lead to a sudden discharge, which can be painful if your fingertip is involved in the discharge. It also might affect the functionality of electronic devices, and it can become quite serious in combination with flammable liquids or dusty solids. So my message is that in many cases, we need to do something against static charge. That is why we need to have antistatic agents. They inhibit the formation of static charge or accelerate its decay. Today, we discuss polyolefins, and as I suppose most of you are experts in the industry, you won't be surprised by this overview of typical antistatic agents in polyolefins. First of all, we have ethoxylated fatty amine. From a purely technical perspective, this chemical compound can be considered the benchmark in polyolefin antistats, so it found its way into the title of this webinar. Well, technical performance is one thing. Ethoxylated fatty amine has been questioned for a while because its product safety and regulation features raised some concerns. We will have a closer look at this on the next slides. Ethoxylated fatty alcohol is a chemical compound that was introduced as a nitrogen-free alternative to ethoxylated fatty amine some years back. So it is for sure interesting to see how both products perform in direct comparison. You will see in a few minutes this chemistry is not a huge step forward with regards to safety and regulations. Lauric acid diethanolamide is another well-known antistatic agent for polyolefins. It provides a better food contact status than the amine. However, still a harmful substance. Glycerol stearates, mainly monostearates, are very safe antistatic agents for polyolefins, but show a quite low performance, with low meaning not long lasting. Finally, an interesting candidate for antistatic polyolefin applications is LOXIOL VPA 1726. It is an established product in our portfolio as an antistat for polyamide and also sintered ultra-high molecular weight polyolefin sheets. The safety and regulations profile is outstanding, and we were curious to learn how the product would perform compared to other antistatic agents in polyolefin applications. So for our study, we picked all these additives except from glycerol stearates. Why no glycerol stearate? Because there is no real need for alternatives to this chemistry. If the antistatic performance is okay for you, continue to use it. It is cheap, available, and safe. On the other side, we do see a need for alternatives to nitrogen-containing antistats, such as ethoxylated amines. I mentioned product safety a moment ago, and I now invite you to have a quick look on the safety data sheets of the antistatic agents. I just took some snapshots of the data sheets of the products we actually used for the tests. So here's the one for ethoxylated fatty amine. And within seconds, you realize that this product requires serious safety measures for transport, handling, and storage due to potential hazards for human beings and environment. It causes severe skin burns and is very toxic for aquatic life with long-lasting effects. Those of you who have handled this chemistry already know very well what it means to have it in the warehouse and in production. When changing over to ethoxylated fatty alcohol, the safety situation does improve indeed, so it's no longer labeled as a hazardous material for human beings, but still for fish or aquatic life in general. Better, but not yet good. For lauric acid diethanolamide, so again a nitrogen-containing antistatic agent, necessary safety measures getting more serious again. Not as serious as for ethoxylated fatty amine, as the product is just, if I'm allowed to say, toxic to aquatic life, while the amine is very toxic, and it causes skin irritation, while the amine causes severe skin burns. However, still a product that requires proper measures for transport, handling, and storage. If we now have a look at the MSDS of test candidate number 4, which is LOXIOL VPA 7026, the situation is totally different. No hazard symbols, no special precautionary measures necessary. This makes transport, handling, and storage a lot easier, which is a great improvement. So what do we take away from these slides? Out of the 4 potential antistatic agents for polyolefins we just looked at, LOXIOL VPA 7026 is clearly the best with regards to product safety. If you're not a master batching company or a compounding company, you have no direct contact to the pure antistatic agent, so its MSDS might not be crucial for you. However, you might be interested in the maximum dosage you can apply to your film or whatever your product is, and still comply with food contact regulations. We have compared the food contact status of the 4 antistatic agents according to US FDA CFR 21 and EU 10/2011. For FDA, we have listed the paragraphs the product does comply with according to the food contact statements of the suppliers, including ourselves. And for EU 10/2011, we mention the specific migration limit that applies for the respective chemistry. For ethoxylated fatty amine, you see according to FDA, you are not allowed to use more than 0.1% of it in a polyolefin film made for food contact, no matter if the antistatic effect at this dosage is sufficient or not. For EU 10/2011, there is an SML, specific migration limit, of 1.2 milligram per kilogram of food. An example. Let us assume you use 1 gram of packaging material to pack 1 kg of food, which is not much. Let us further assume you put 0.1% of ethoxylated fatty amine in the film, as allowed by FDA. Then you have 1 milligram of additive per 1 kg of food. If you assume worst case, which is full migration of additive from the film into the food, you are rather close to the EU limit already. So FDA and EU 10/2011 are pretty much in line here. For ethoxylated fatty alcohol, the food contact statement we have lacks any information on FDA status. I need to mention we have the 2018 version in our hands. I cannot tell if there is an updated version available, but according to the version that I have, it does not comply with FDA regulation. The SML in EU 10/2011 is slightly higher compared with the amine, which is no significant benefit. The food contact status for LDEA is distinctly better. The percentage which can be used within FDA regulations is higher, and the SML in European regulations is higher as well. However, there is still a limitation. With regards to food contact status, none of these 3 additives compares to LOXIOL VPA 1726. From the chemical composition, the product would qualify as a direct food additive. In other words, you could add it into food, not only into food packaging. However, important to mention, we do not produce food additives, so LOXIOLs are only marketed as additives for food packaging, so for indirect food contact. Nevertheless, this shows how safe this chemistry is. As a consequence, EU 10/2011 does not set an SML, so you are allowed to use as much as needed for your specific application. In a nutshell, LOXIOL VPA 1726 provides a tremendous food regulations benefit compared with the other products. Now, we still need to prove it provides a decent antistatic performance as well. And here's what we did. All process steps were done in our technical development center. First, we created additive master batches on our compounding extruder using a liquid feeding system. These master batches were used to extrude films on a single screw lab extruder and to produce injection molded plaques. And finally, we determined surface resistivity of the films and plaques in order to evaluate the antistatic performance. Some more details on the next two slides. First, some details on the materials. We started with polypropylene films and tested two different grades of polypropylene. The first one is a random copolymer, so a PP with a few percent of ethylene copolymerized with propylene. It is typically used to form the outer layers of a multilayer film. The other one is a homopolymer PP, which could be used for the core layer of such a film. Important to mention, we made single-layer films. All four antistatic agents were incorporated into these two polymers to form a master batch with 1% active and then a film with 0.5% active. A master batch with 1% of antistatic agent. You will rightly raise the question, why such a low concentration? It is because film extrusion was done using a single screw lab extruder, and we needed to make sure the antistatic agent would be properly dispersed in the film. So using a 10, 15, 20% master batch for a final concentration in the film of 0.5% could have led to an inhomogeneous distribution of additive within the film, leading to antistatic figures which are not reliable. This is something we needed to avoid, so we used a very low master batch concentration and therefore a high master batch dosage. This is something you, of course, would not do on big scale. Actually, we made the same process with LDPE films, but only with ethoxylated fatty amine and LOXIOL VPA 7026. You will learn soon why we skipped the other two. Finally, we did injection molding, again with two different PP grades. The master batch concentration was higher in this case, as the extrusion and injection system in the injection molding machine caused a better mixing than in lab extrusion, so we could use a master batch concentration which is a bit closer to what is done in the real world. Important to mention, we always used the same polymer for master batch preparation and extrusion or injection molding, so we avoided any influence of blending polymers. So now we have the test specimens, how to test them. First of all, we stored them for defined periods of time and then put them into a climatic chamber with standardized and constant temperature and humidity conditions prior to measuring the surface resistivity of these films or plaques. So by comparing different storage times, we were able to analyze how surface resistivity and so antistatic performance would change over time. And by picking one certain storage time and conditioning the samples at different climate conditions, we were able to analyze the influence of climate, or more specifically, the influence of humidity. So we are ready to start the next chapter. First, I will show you the results of our tests in PP films. We tested two PP grades, and I'll show you the influence of time and the influence of humidity for both. Makes 4 slides. For the PP film section, I will give a brief intermediate summary. Okay, first chart, PP random copolymer films, influence of storage time. What do we see? We see a bundle of columns for each of the 4 antistatic agents. On the left, we see the surface resistivity indicating the antistatic performance. So the lower the columns, the better the antistatic performance. And this antistatic performance was measured after certain storage times. Results. Ethoxylated fatty amine, LDEA and LOXIOL VPA 7026 provide an overall similar antistatic performance. There are some ups and downs, but there is neither a significant difference between those three nor a trend. Additive migration is obviously quite quick in these thin films, so the performance is there right after extrusion without waiting the additive to migrate. Ethoxylated fatty alcohol, which is claimed to be a substitute for ethoxylated fatty amine, does not work at all. You need to know the upper end of our measuring range is 10 to the power of 16. And that's where the ethoxylated fatty alcohol films are. So no antistatic performance here. Same films, but now we are checking the influence of humidity. Ethoxylated fatty amine, LDEA, and LOXIOL VPA 7026 show a good and relatively similar performance. However, looking only at the yellow columns, we see a slight tendency for LDEA and even more for ethoxylated fatty amine that resistivity increases for low humidity. Ethoxylated fatty alcohol, as seen on the previous slide already, does not show an effect. PP film chart number 3, we are now in PP homopolymer, and again look at the surface resistivity at different storage times. You see for each product, the initial figures are very high. Only after 3 weeks storage, the resistivity is on a good level. If you recall the diagram 2 slides before, this was not the case for random copolymer PP. The reason is that homopolymer PP is more crystalline. That is why migration rate of the additive is reduced. After storage for 3 weeks or longer, however, the resistivity level, which is reached by 3 out of the 4 antistatic agents, is comparable and good. Ethoxylated fatty alcohol does not work. Again, I must say. The light blue column for ethoxylated fatty amine on the left-hand side indicates a very high value. This average value for surface resistivity shows an ultra-high standard deviation and should not be considered. But I also did not want to just leave it out. The reason for this high standard deviation, unfortunately, could not yet be identified. Final results slide on PP films, homopolymer, and influence of humidity. And now let's start on the right-hand side. LOXIOL VPA 1726, antistatic performance is good and not depending too much on humidity. LDEA, the same. Ethoxylated fatty alcohol, in line with previous results, no performance. Ethoxylated fatty amine, strange. The result at standard humidity 50% is in line, but at 15 and 80% it is at the upper end of the measuring range. Standard deviation this time is okay. So considering the odd result on the previous slide, we have to assume we had a problem to properly disperse this additive in the film. We are still looking at this. I'm not able to provide a definite explanation now. However, I do not relate this to the performance of the additive as such. Before I start with the PE films, I'd like to briefly summarize and conclude what we have learned so far. By checking MSDS and food contact information, we know that LOXIOL VPA 7026 is the only really safe product among the 4 additives. I indicated this here in green, red, and yellow, symbolizing good, bad, and in between. I know this is a pure helicopter view, but we have discussed the details. Antistatic performance-wise, I consider ethoxylated fatty amine, LDEA, and LOXIOL VPA 7026 good solutions for PP films. Ethoxylated fatty alcohol does not work at all. So how to continue? We decided to exclude ethoxylated fatty alcohol from further testing. It is not a safe, and we found it is not a well-working material in PP films. What about LDEA? It works well, yes, but would you use it to replace ethoxylated fatty amine? Where would be the crucial benefit? You would replace a material which is not safe by another material which is not perfectly safe too. That is why we excluded LDEA from further testings as well, and only compared ethoxylated fatty amine and LOXIOL VPA 726. So far, LOXIOL has proven to be a safe material that can compete with the amine performance-wise. Hope you are curious to see further results. In PE, we continue with 2 result slides in PE films, antistatic performance depending on time and on humidity. Storage time. You see we have less columns as we check just 2 antistatic agents instead of 4. And you see the antistatic performance is overall similar. Comparing the dark blue columns, ethoxylated fatty amine shows a higher resistivity value right after extrusion, then coming down to a little lower level than LOXIOL VPA 1726. Remember, we used a very low dosage of antistatic agent here, just 0.1%. You for sure can go higher than this to adjust the effect further if needed. So we are not seeing any crucial difference. PE films once more. Now we look at the influence of humidity. Interestingly, a similar picture as on the previous slide. LOXIOL VPA 1726 is more stable in performance. Ethoxylated fatty amine shows a slightly better performance at mid and high humidity, but it has a problem at dry conditions. We have seen this to a minor extent in PP films already. Good, let us leave PE again. Last application is PP injection molding, plaques in this case. We tested 2 different PP grades again, random copolymer and homopolymer, but different ones than for film extrusion. We have 2 result slides, antistatic performance depending on time for both polymer grades, and we waived testing the influence of humidity this time for capacity reasons. Here are the results in random copolymer PP. No big differences, and same conclusion as before. Ethoxylated fatty amine, lower minimum resistivity, LOXIOL VPA 1726, more stable performance. Honestly, we had expected the plaques to require some more storage and so migration time to provide a decent antistatic effect, as the plaques are much thicker than the films, 3 millimeters versus 30 microns. However, this is not the case. Even the plaques that were tested after 1 week, plus 48 hours in standard climate, are more or less on the final level. Our explanation is that in injection molding, the polymer is kept molten without strong friction for a few seconds, and the additive has the chance to migrate in this state a lot more quickly than in solid state. In comparison with injection molding, the film in extrusion is cooled down more rapidly, so migration needs to take place mainly in solid state. Homopolymer injection molding. The bad thing is, I cannot tell you anything really new here. The good thing is, the results are consistent. Ethoxylated fatty amine, lower minimum figures, LOXIOL, more stable performance. Well, after this long series of slides full of results, I hope you're still with me and you are ready for the final summary and conclusion. The table here again provides a helicopter view, a very high flying helicopter view, as all the details have been provided in the last 20-25 minutes. We know that ethoxylated fatty amine and LOXIOL VPA 1726 have not shown an identical, but an overall quite similar performance, with some benefits here and there for the one or the other product. Ethoxylated fatty amine might provide some lower minimum values for surface resistivity, but performance, on the other hand, is more influenced by storage time or film age and humidity. But overall, both products are well-suited antistatic agents. What really makes the difference are the safety and regulations aspects. We have compared the safety data sheets, and you remember the hazard pictograms for ethoxylated fatty amine and the safety measures that need to be taken. Furthermore, you have seen how critical it is in food contact applications. And you remember the safety data sheet of LOXIOL VPA 1726, which actually just states the product to be safe. The product is fine for food contact without any restrictions. These are substantial benefits. So keeping all this in mind, I personally consider LOXIOL VPA 7026 the superior product. And I hope I was able to convince you as well. The key takeaways. LOXIOL VPA 7026 is 100% based on naturally derived raw materials, and not only 100% natural, even 100% vegetable. So it is a sustainable additive, it is a safe additive, it is a high performance additive. So I can say it's a true green polymer additive. Ethoxylated fatty amine is, from the technical perspective, a good product, no doubt. But from safety and regulations perspective, it is not. All the work and all the results I have presented to you were generated in our own lab. I can tell you that the product in the meantime has been tested in the real world as well, and the results were confirmed. Do you look for a proper replacement for ethoxylated fatty amine and polyolefins? As you are attending this webinar, I guess the answer is yes. So why don't you test us and our product in your master batch, in your film, whatever you are doing? I'm looking forward to getting your feedback. And I'm looking forward to your questions, your remarks, and your comments you have entered via the chat function. Thank you for the time being. I now hand over the microphone back to Jana.
Thank you, Christian, for this very informative presentation. As mentioned before, now is the time for questions that have been asked during the presentation. If you did not have the chance to think of any questions yet, please ask them now using the questions section to your right. If any of your questions cannot be answered within the session, I'll make sure to contact you later on. I'm also happy to receive any kind of feedback about the presentation or the webinar in general, as this will be the only way how we can improve our webinars. Here comes the first question. What is the maximum percentage of LOXIOL VPA 1726 that can be added to the master batch?
Good question. I would say 15% should be a realistic target, could be up to 20%, but this requires testing using the specific polymer which should be used for master batch preparation. A migrating additive is of course not easy to incorporate, as the additive does not know when we want it to migrate and when we want it to stay in, but that's the case with any migrating additive in a master batch. So again, 15% plus can be recommended, but storage test of the master batch is recommended as well. However, we have seen that 0.1% in polyethylene films is sufficient. So please consider 15% in the master batch could also be too high, as an improper distribution of the additive in the final article is adverse for the effect. So it depends on the polymer, the application, and the final dosage in the film, for example.
Oh, thank you very much for that answer. The next one is a good one. What does VPA stand for?
If I recall correctly, it's the German wording for trial product anesthetics. Versuchsprodukt Antistatica in German. So trial product antisthetics.
That's what I thought so too. Thank you very much for that answer.
Long time ago, I have to say.
The next question is, where is LOXIOL VPA 1726 produced?
It's currently produced at our German site, but it can be produced at every Emory site.
Thank you. I have a question regarding the sample storage. Did I understand correctly that the films and flakes were not stored at defined climate conditions?
Yeah, the test specimens that we made, yeah, the films and flakes, that's correct. They were stored in the lab, so at quite constant, but not strictly defined climate conditions. So just for 48 hours prior to the actual measurement of the surface resistivity, the samples were stored at these defined climate conditions. Reason for this procedure, honestly, is simply capacity. We just do not have enough climatic chambers to store the samples there for weeks or months. or even 1 year in one case, especially as we have also other projects running requiring standard climatic conditions as well.
Thank you very much. The next question is, any idea of the VOC profile of LOXIOL VPA 1726?
We just know that this product it was actually not invented to be a substitute for ethoxylated fatty amine, but it was invented as an antistatic agent for so-called engineering polymers or engineering plastics. So its current main application is polyamide. And polyamide, as you all know, has a very high processing temperature. And for this application the product is used and it's successful. So the VOC content is low without being able to give you any defined number.
Thank you very much. The next question, how is it in comparison with LOXIOL 1010?
Funnily, LOXIOL 1010 was actually part of the webinar, but it was undercover, so to say. The product I mentioned, LDEA, lauric acid diethanolamide, that's LOXIOL 1010. So when you want to know how LOXIOL 1010 compares with LOXIOL VPA 1726, I recommend to watch the recording of the webinar.
Thank you very much. And here you see another question. What is the viscosity of LOXIOL VPA 1726?
Yeah, quite important for liquid feeding. Viscosity of LOXIOL VPA 1726 is about 1000 millipascal seconds or 1000 centipoise at room temperature, 20 degrees. Now, what is 1000 millipascal seconds? Just to give you an idea, olive oil is about 100 millipascal seconds. Honey is about 10,000 millipascal seconds. So the LOXIOL is in between. Of course, when increasing the temperature in your liquid feeding system, which is something we anyway recommend, the viscosity of the product will be reduced. And we provide, by the way, a respective curve viscosity as a function of temperature in our technical data sheet.
Thank you very much, Christian. The next question is, in which other polymers can LOXIOL VPA 1726 be used?
Actually, it was developed to be an antistatic agent in the so-called engineering plastics, so polyamides, for example. By coincidence, we found that it was well working in these ultra-high molecular weight polyethylene sheets as well, which are not extruded, but which are sintered due to the high molecular weight of the polyethylene. And so it can be used in many different polymers. It's a very thermo-resistant material. So actually it works in many different polymers. The application in polyolefins is a quite recent finding of our R&D and application technology.
Thank you very much. Is there a difference in performance in PE films produced by cast or blown films?
Honest answer, I do not yet know because I have no feedback from this real world I just mentioned for PE blown films. What we have done is similar to in the lab, is similar to a cast film process. So I can answer the question for cast films, but the comparison to blown films, I cannot comment on that. But I expect it would work also in this application. Maybe the dosage need to be adjusted, but this has to be tested anyway.
Thank you very much. The next question is it safe to use it for electrical parts for packaging because of the corrosion?
Yes. You've seen that the ethoxylated fatty amine MSDS was mentioning the product to be corrosive, which could be a problem for electronic devices if you have some migration to the surface of the film. This is not the case for LOXIOL VPA 1726. As I mentioned, it could be, in theory, used as a direct food additive. So you can eat it if you like.
Thank you very much. Do you have some experience with using VPA 1726 in LTPE films when printing steps follow after the film extrusion?
Again, not yet, I have to say. But honestly, there is, of course, an optimum level of antistatic agent used in this application. But it's clear that migratory additive will be located at the surface of the film. So when you have too much of antistatic agent on the surface of the film, printing will be affected. Yes, that's definitely the case. On the other hand, an antistatic agent also increases the surface tension of the film. So it's true, you need to have a closer look at this, but I do not expect a big problem because, as I said, the product is not brand new. It was just tested for this new application. And in other polymers, we have not made some bad experiences with printing and this antistatic agent.
Thank you very much. Since I do not see any additional questions anymore, we have now reached the end of our session today. So thank you very much for your questions and feedback, and to Christian for today's presentation. I really hope you enjoyed today's webinar. You will receive a link to the recording of today's session within the next few days. And just in case any questions come up later on, please respond to that email. I also love to receive any kind of feedback or suggestions for improvement, and also proposals for our next topic. So thank you for taking your time to attend this webinar, and I hope that I can welcome you to our next presentation. I wish you a wonderful day. Goodbye.
Thank you very much and goodbye.